So we now move on to greenhouse gases, and our symposium session chair is Dr. Geoff Hurd, who is the science advisor for our Threatened Species Index in TERN. And Geoff is also an affiliated researcher at the University of Queensland with the Centre for Biodiversity and Conservation Science, and also doing research through ANU Fenner School on spatial and temporal dynamics of declining species, looking for insights into population processes that can guide conservation planning. You can see we had a method here. We decided to mix up all of our session chairs so they weren't chairing a session about which they knew anything, just to add some interest. Over to you, Geoff.
Thanks, Beryl. So we've got four terrific speakers today. We're going to talk to us about greenhouse gases, carbon cycling, nutrient cycling, ways of measuring those, both for the benefit of understanding environmental change in Australia, but also for its benefits to agriculture. And we're starting off with Claudia.
Thank you. Good morning, everyone. I'm Claudia. I work at CSIRO, and I'm going to shift a little bit of the focus, and I'm going to talk about soil organic carbon fractions in Australian landscapes. Okay, let's see if I can work this out. Okay. I would just like to start by acknowledging the traditional owners of the countries. And so, as the Joint Research Centre said in one of the latest reports, it's time to pull up our socks. But we know that only looking at the total soil organic carbon, it's insufficient for understanding soil organic carbon turnover and stability. We know that soil organic carbon consists of various functional pools. They exist at different stages of decomposition and extent of interaction with mineral phase. And they both can influence soil turnover time and stability. We have a more labile pool, which is important in terms of nutrient recycling. It's readily available to microorganisms, and during mineralization, they release nutrients for the plants. And we have a more stable pool, which is important in terms of climate change mitigation, because the carbon that it stores, it stays into the soil, hopefully. Why is the assessment of these different fractions crucial for? Because it provides mechanistic understanding and modeling of the soil decomposition. It helps us to understand the stabilization processes and the storage capacity. And it helps us also with the initialization and validation of the greenhouse gases emission models. As we know, the Fulcam model used for the land sector accounted in Australia. And also, it can also help us with the computation of ecological monitoring indexes in landscape resources. There are different types of fractionation that are used all over the world. The problem is that there is no agreed methodology in the scientific community. This makes it different to compare the data from different types of fractionation. And some of them, they are difficult to replicate because they require sophisticated lab instruments. And they are generally expensive and time-consuming. So in this context, recently the thermal analysis gained a lot of interest. Thermal analysis per se, it's not new, but what is new, it's its application in the soil organic matter fractionation. So what we try to do with our work is to compare what we call the CSIRO fractionation method, that it's physical fractionation combined with NMR characterization, and compare it with the results of the thermal fractionation. So I'm going to try to walk you throughout the methodologies. So we start from bulk sample that are, so it's soil sieved at less than 2 millimeter. We first do a physical fractionation at 50 micron, and this leads to the separation of coarse and fine fraction. Then these two fractions, they are first analyzed with the NMR. And from the results of the NMR, we have the labile fraction in the the labile part in the coarse fraction, which we call POC, from particulate organic carbon, and then the stable part also in the coarse fraction. And then we have a labile part in the fine fraction, which we call HOC. POC is considered to be the more labile one. HOC is considered to be a bit more stable. And then when we sum together the stable part in the coarse fraction with the stable part in the fine fraction, we have the ROC, which is the resistant organic carbon, the most resistant part in our soil sample. And then, again, with the coarse and the fine fraction, we analyze them with the thermal instrument. And we have, again, the labile part in the coarse fraction, which in this case we will call TOC 400 because it's combusted at 400 degrees, which should be the equivalent of the POC fraction. Then we have the labile part in the fine fraction, which we call TOC 400 again, which should be the equivalent of the HOC. And then we have, again, ROC, which we will call ROC 600 because it's combusted at 600 degrees. This is based, the NMR characterization is based on the Baldock et al. Methodology. And yeah, we try to put it all together and to look at the deviation and alignment between the two methods. For this, we use a total of 111 samples that were collected in the framework of the SOCOM project from different pedoclimatic conditions across Australia. They come mainly from agricultural sites. Under TERN, we are trying to expand it to natural ecosystem. This is still a work in progress, but we try to test the methodology. And what I want to mention in this slide is that the sample, they come from both standard and detailed side. It means, so in a standard side, we collected 3 soil cores that were mixed together from the plot, while the detailed sites, the three samples that were collected from the same plot, they were kept separate to see if we have spatial variability in the same plot. Some of the results. So we have some violin graphs on the left with the results of the CSIRO fractionation, on the right with the results of the thermal fractionation. What I think is interesting is that we can see that among the 70 and 80% of the soil organic carbon, it's mainly labile, and the remaining it's ROC. And what is also very important is to see that we still have a very high percentage of labile carbon in the fine fraction. It's not only a resistant carbon. Then we looked at the total organic carbon in the coarse and in the fine fraction. So we have on the x-axis the total carbon from the CSIRO fractionation, on the y-axis the results from the thermal fractionation. And just a bit of information, the lean concordance coefficient goes from -1 to 1. 1 means good agreement. So this is what we are aiming for. And the root mean square error should be as low as possible. We are pretty happy with the results. This is in the core and in the coarse and in the fine fraction. We are pretty happy. And here we have from left to right the comparison for the POC, HOC, and ROC fractions. POC and HOC, they look pretty good. With the ROC, it gets a bit messy, as you can see also from the R-square and the other model performance indices. So what this means, the initial results suggest that developed method can be used to generate cost and time effective fractions. The stable forms, so the ROC from the thermal approach, are a bit lower with the thermal fraction compared to the CSIRO method. We are working on this and we are trying to understand why. Of course, they are different instruments, they kind of look at different things too, but we are trying to understand what's behind this. And the advantages of the thermal analysis is this: it's high throughput and it only requires 30 minutes per sample, and it requires a very low amount of pre-processing of the sample. So in a very low amount of time, we can generate very high-level data sets that include very specific information, not only about the soil organic carbon, but the fractions of the soil organic carbon. And the nicest part, I think, is that it has very low detection limits, and this allows us to do the fractionation also in ecosystems like the rangelands that have a lower amount of carbon, and, for example, in which the CSR fractionation cannot be applied because of this. And some of the limitations that we have identified during the testing, it's that it can't really directly measure the inorganic carbon. We really hope for it. It should have been decomposed at 900 degrees. Sometimes we have some more unstable form of carbonates in the soil, and they are combusted at lower temperatures, so then it makes a bit of confusion with the ROC. And it kind of sometimes it overlaps of chemistry in relation to the temperature thresholds, because it's a stepped method, and so it can influence a little bit. Okay. Thank you very much for your attention.
Thanks, Claudia. That was terrific. Next up, we're going to have David talk to us about eddy covariance towers. Just a reminder that we will have our Q&A as a panel, so please get your questions in through the app or email them to beryl.morris@uq.edu.au. Thank you. Thanks, David.
Thank you very much. So, yeah, I'm here today actually to introduce a new TERN capability. So introducing the Australian Long-Term Agroecosystem Research Network. I'm from Queensland University of Technology. I've been involved in TERN since the beginning, back in 2010, and so quite familiar with these TERN tools. I've also been an agricultural researcher, so working in the ag space, but also a farmer. And it's been quite frustrating me for the last decade or so, seeing all these really powerful tools that we have in TERN that aren't translating to what the farmers have in front of them to make decisions. So that really inspired us to try and do that translation piece of actually how do we actually get these really cool tools out to the managers of 50% of Australia's land mass. And if you include Indigenous managers, even more. So that's sort of what set off this little network of ours. So very, very briefly, we look at emissions from a farm. So, farms are very complex beings. They vary greatly across all of Australia, different climatics, different soils, different management. And each of those different managements leads to different emissions of greenhouse gases. These are all very complex, all multiple sources. Particularly in northern Australia, we have very little data on what these sources and sinks look like. And yet, at the same time, farmers, particularly by supply chains, by government mandates, by society in general, are expected to be able to capture all this information, report it up through their supply chain, and eventually try and reduce those emissions. And this is in places where, if you look at particularly around the soil organic carbon, our previous speaker just alluded to how complex that was. We're looking at how do we actually, do something about, mitigating some of these emissions and looking at storing carbon into our systems. But we need to have long-term data sets to be able to show, is that possible? What forms is that soil carbon stored in? And ultimately, what management options are available to, make sure that that carbon stays there into the future. All this stuff together, we can't look at these things in isolation, so this is all the things we need to capture. So it's very, very complex, and farmers are getting bombarded from multiple angles, and there's not a really good data repository, independent sources of information to really help them there. And this is getting more complex by the fact that we now have big multinationals pushing for basically this reduction in carbon on farms. And so there's two major splits between how you go at the moment if you wanted to basically look at reducing your farm emissions. So carbon offsets, where the farmer sells their credits to somebody else. It might be McDonald's, or it might be the Australian Carbon Credit Scheme, which goes into offsetting emissions from coal mines and the big polluters and whatnot. Now, this, what we call the regulated market, is, as it says, highly regulated. There's very, very in-depth methodologies there. They've been developed over the last 15 years and they're very rigorous, and yet it is a mess. It is very, very complicated. It's very, very expensive. You've got academics criticising governments. You've got sequestration rates that are not possible, biologically being credited. And so if we have this really complex, really regulated system, once we get over to this side, which is what we call the unregulated market, it's really going to be the Wild West. So this is where actually companies themselves are defining how they define sustainability. And this is just around carbon. We haven't even talked about natural capital biodiversity. So understanding what management impacts farmers can do and what the implications are in that long-term framework is really, really critical because farmers at the moment are just getting confused. So my slides have been completely messed up, but anyway. One of the things here is, why do we care about this? Well, because there are really big potential options there as well. So soil carbon, talked about in the last slide, we can get really good sequestration rates. So, if we're looking at two of the major practices that we can do in Northern Australia, perennial legumes, so that's bringing in new species of deep-rooted legumes, or improved grazing management, we can get, that 0.3 to 0.6 tonnes of carbon sequestered per year. So what does that mean? Well, not much, unless you put it into the context of, well, for beef to be carbon neutral, you only need 0.1 to 0.6 tonnes of carbon per hectare per year. So that's why, we've got this really complicated system, we've got this really complicated thing, we're trying to store things with huge amounts of climatic variability over long periods of time, but because there's so much potential there, it's really driving that forward, and so that interest is not going to go away, but we need to make sure, given that if we sequester it into the soil, it needs to stay there for 25 years, that we have some confidence it's going to stay there for 25 years. And this is just a graph that sort of highlights our climatic variability that we have. So this is from down near the border between Queensland and New South Wales on the grazing property. You just saw our ENSO cycles driving our rainfall. That obviously drives our biomass. So we're talking about a 5-year carbon window here, and this is actually a commercial property that got credited carbon under the Australian Carbon Credit Unit Scheme. Now they measured in 2016. We started measuring here in about 2019. So we measured right in the height of the drought. And so as we sort of expect, we see biomass follows rainfall. Now, 2022, that farmer came back, sold a couple $1 million worth of carbon credits. So, fantastic for the farmer. But are we sure that those carbon credits are going to stay there, that soil carbon is going to stay sequestered into the ground? Well, unfortunately, it doesn't look like it. So at the moment, because we don't have these long-term data sets, we don't understand how the particular management, in this case we're looking at improved grazing management, will influence that storage of carbon into the future. You're just creating a whole bunch of uncertainty for a whole different, from the farmer to the government, research organisations all the way through. So we really need to get a handle on how do we actually make soil carbon credits work. We can replace that with soil carbon insetting or natural capital insetting, whatever it might be, but how do we actually tie that management practice back to the outcome of either soil carbon or natural capital in this really dynamic climate that we have here in Australia. So Elaine Mitchell and a bunch of us wrote this paper outlining how can we actually make this system work. And one of the things we recommended was, we need to set these reasonable bounds. We need to put some guide rails around what this looks like for the industry. And part of that was establishing these independent monitoring sites that hopefully become long-term, so we can keep this going into the future. So that was basically, the emphasis for ALTAR. So what is ALTAR? Well, we mentioned flux towers before. Flux towers are one of the key components of it because it really allows us to dive deep into that carbon cycling. Now, flux towers alone don't give us soil carbon, so there's also, we do regular soil carbon monitoring, we measure other greenhouse gases, so back to our farm at the beginning of my slides where we have to capture all those sinks and sources. We're also measuring natural capital. So we're basically trying to measure all these things together. Now we do that in a paired site approach. So we actually have two managements, a business as usual, plus an improved management, which allows us then to tease out those climatic variations from our actual management. And you can sort of see here in this example here where our yellow line here on the bottom graph is actually our improved management. And you see, great, it goes up through the roof. This is just NEE, so lots of carbon going into the system. But if we didn't have that green line, which is our business as usual control, we wouldn't actually know that, how is that tracking actually against, well, what would happen anyway? And if we actually normalise that, we actually see whatever that spike that drove that carbon sequestration at the beginning was not sustainable, was not sustained over the longer term. And so we've got to question, well, is that long-term management actually going to lead to increased carbon in our system? So this paired site approach is really, really critical to be able to separate out those climatic impacts from the management. So what is ALTAR? Well, it's a collaboration between TERN, QUT, UWA, the Zero Net Emission CRC, which is one of Australia's largest CRCs, and a whole bunch of Indigenous groups, pastoral companies, and some international institutions as well. Independent open access. Open access comes with a bit of a caveat around privacy, so we have to be conscious of, this is data now on private lands. This is not public lands, and particularly around the management data, some of this is really sensitive, and the Indigenous frameworks really, hold a good sort of case study for how we should proceed with that. But it's no different from working on just farmer properties as well. So the idea is we support industry, we support better decision making, and we provide that feedback. So, well, what is actually that management doing across that landscape, and particularly in that long term, that picture. And by doing this sort of business as usual versus improved management approach, whether it's grazing management, Indigenous knowledge, woody regrowth, whatever it might be, it allows us to really sort of tease those things apart. A key thing is we see this technology taking off in this space more and more as we move towards that 2040 targets. We need to the whole industry needs to decarbonise, so these technologies are going to take up, so we need to have those standard protocols, and particularly for modelling. Co-design is critical. So we talk about sustainability of funding. If we can get industry engaged, if I can get the local landholder out at Barcolden, which is 14-hour drive away, to go and clean a sensor for me rather than having to send someone out from Brisbane, it really decreases those costs. It means that we're more sustainable. And ultimately, what we basically have is a whole toolkit through what TERN has been generating, including all the stuff we heard in the last sessions, that we can basically tap into. And here is our website, recently launched, and so we'll be populating this as we go along. At the moment, we've got basically 10 sites, and working with our partners, and particularly the Zero Net Emission CRC, we'll be looking at expanding those sites, a lot over the future. So thank you very much.
Thanks, David. Next up we have Chiara. Am I pronouncing it correctly? It's going to talk about carbon and nitrogen tracking, I believe.
Thank you, everyone. Well, my presentation is actually falling quite nicely after the last two, because we're trying to put everything together in a process-based model to trying to track and plan in advance to this changing of nutrients of carbon and nitrogen. So first I would like to begin by acknowledging the Kaurna people as the traditional owner of the land where my research takes place, and pay my respect to their elder past and present. As we talked in the last couple of presentations, we are very interested in measuring, monitoring, and evaluating, but also planning. And process-based models are kind of the perfect tool to understand how nutrients flow through the environment from above ground, so both in agriculture, but also natural ecosystem, to the soil. And soil is probably one of the most important in terms of greenhouse gas emission, because it's very hard to understand how nutrients falls into the soil because of the long-term capacity and storage of those nutrients. Anyway, Australia has signed for net zero emission by 2050, so we need to start planning the right way to go towards that path. Also, tracking nutrients is very important for understanding the land condition and the long-term sustainability. Agriculture is affected to climate change. Understanding how nutrients, particularly nitrogen, and their relationship with carbon is very important to maintain and sustain yield and also maintain agricultural productivity in terms for the farmers. Another important part is as mentioned before in the second presentation, is we're seeing an increased interest in carbon accounting. We have to be sure that whatever we measure, we plan and monitor is accurate as much as we possibly can. So having models is always very interesting to play around with. With this framework, what we were looking at is how nutrients flow through the environment. The environment seems pretty easy, either agriculture or natural ecosystem. Here is a savanna. It seems easy, but when we start going into a process-based model, we have to characterize every single piece of the puzzle, which start making it look like this. And this is not even the most complicated models that we can see. But in terms of above ground biomass, we kind of get good understanding so far. At least models are good performances. And we go from living biomass, so stem, leaves, branches. We know perfectly how this goes into the fall, either for natural causes or because of fire, burning, different type of grazing agriculture, and get into the litter or that material. And then how those one falls into the soil. As you can see, above ground biomass kind of sort of easier. Don't take me wrong, it's hard, I know, but it's easier to measure and monitor because we can actually see and take it. And also their turnover time is very short, so we can detect change within sometimes even months. If we get into the soil, it's always characterized a little bit with, there's pools, one fast, one slow. It's very hard. Soil change could take hundreds of years to change, so detection and characterization of what drives soil has always been very complicated. And when we start putting together carbon and nitrogen, things get even more messy. So there's a lot of challenges, and I'm not going to the deep characterization of carbon as Claudia described it before, but just to some of the challenges. Soil carbon modeling has been there for at least 30, 40 years. But carbon and nitrogen has been a little bit more limited because they've always been finding problems. As you can see, if parameterization before was high, when you start putting also nitrogen, it gets even higher. Because of as I say, most of the carbon model, especially for a landscape scale, has been done during 90s, where computer power was quite, at the beginning, it was not that well, and now we start having much more power. So some of the representation that now we can, is solid science, they're still not representing the current models, especially on the landscape. And also what we can see is the cost, despite costs of management are high, we still have been looking at a lot of data availability, but the quality is poor and it's very difficult to put them together. So in this kind of project, we're trying to find a framework, a general framework, not for a specific model, to put together data to improve some of these carbon models. In particular, we're interested in microbes and termites to include them in soil organic models, soil organic carbon models. I'm not talking about termites, there will be a presentation the next following days, but microbes are very important. They represent 1 to 5% of the soil organic carbon. Despite most of the models say that all the cycle is driven by microbes, they don't include it into the reaction, which makes, especially right now, we've seen some of the models including it, and not having much effect in the short term, but extremely big effect in the long term. So this is one of the areas that we want to focus. The second one is define a maximum capacity. Soil cannot store infinite carbon or nutrients in general, despite most of the models currently do it. So trying to understand which one is this maximum capacity and how that is affected in the landscape area. The third one, as I said, greenhouse gas emission, like the presentation before, is not just CO2, but all a mix. It's solid science now that you need nitrogen to build carbon, and water is very important because it drives what type of reaction happens. Another important thing that I think came out in the discussion panel before was going below 30 centimeter. Yes, the first 30 centimeter has 80% of the soil, but if we're talking about long-term stability of nutrients, is what happened below. And now climate is changing, practice are changes, land management practice are changes. What does means on the long-term stability of that soil? Another important part is the landscape interaction, especially in catchment where there's high input agriculture, like maybe cotton or some others, what that affects on the lower part of the catchment, nutrients go and move. The last one is data. Sorry to put this one before lunch, I hope no one gets super hungry, but we, as most of us, spend 90% of our time just looking for data, cleaning the data, make them consistent what you already have, and repeat. So trying to find a way and leverage something that we can sure that is done with the same protocol, is consistent across the large area. And so the project is trying to address all of this. Big project, involve a lot of people. And sort of we're trying to build this one within the umbrella of the TERN. So we're not trying to reinvent the wheel. We know this model, they already do this, and we just want to test it and verify on a large scale. So we have different soil modules, vegetation modules, landscape, microbial, and termite. The only one we're probably developing new is the termite one, and put them all together for a terrestrial ecosystem model, sorry. And perfectly will fit into the ecosystem process platform, which has all the super sites where we can constrain above ground and below ground quite well, which means it's a perfect site to calibrate and validate. But also we can use the ecosystem surveillance plot, which are more than 200, where we have soil sample, vegetation type, litter, quality and quantity, which is perfect to drive what goes into the soil. And also we have consistency because a lot of this data has been used for the landscape platform, which then can be plugged in to landscape analysis, which perfectly close the loop and will then go into reporting, but also provide, if the new data are coming, improve science, these different knowledge and processes, we can repeat the process and improve the framework. In this one, we can help to build scenarios as well. And we'll create a cross-platform. What is very important is to keep in mind also the scale of application. Different models answer different questions at different time and different space, and we have to pay attention on what exactly we want. That's I always want to stress these models are always very useful, but we need to pay attention. And so this is a very big project. It's finished first year planning and testing, but we still have a lot to go for the next few years. Another important part is the uncertainty analysis. We know models are quite always wrong, but we need to check where are we falling into the uncertainty. But also it will help to understand where we need more data, where we need more sampling, and create, for example, networks for the agriculture flux tower that would be perfect to fix that gap. And it's a long-term process. Well, that's all for me. I'd like to also thank all the team. I'm just here speaking, but as you see, the project is quite big and involves a lot of people. Thank you.
Thanks, Chiara. Keep those questions coming. We've got 3 currently, so yeah, please keep them coming through the app. And just put who the question is for. That'd be quite helpful for me. So next up we have Anne, and Anne's going to tell us about flux variability.
Thank you.
Alrighty. Thank you, everyone. And just a heads up, I was warned there will be some funky formatting going on in my talk as well. So my name is Anne Griebel. I'm working at the University of Technology in Sydney. But while I present, I do want to acknowledge all the contributors to this talk, particularly Nicola Leaf and Cecilia Evans, who've done the hard work on crunching all of the data. But I also want to acknowledge all the site PIs who have generously shared all their data on the TERN-OzFlux data portal that we've been using in this talk. I also would like to acknowledge the Gadigal and the Dǎmǎtîrcǎ people upon whose lands I conduct my research and where I work. Okay, so far it's looking good. So let's introduce you to the TERN-Ecosystem Processes platform. You should probably be familiar with it by now because Dave already touched on it briefly. But we have this network of flux towers that are continuously monitoring carbon, water, and energy exchange. So it's kind of a collaboration of individual sites who collect the data at their individual stations, but then they upload it to the TERN data portal where it greatly increases the value of the individual sites. The flux towers are located in a broad range of ecosystems and in various climate zones, and there's obviously considerable variability between sites in how much water or light they can access. So in recent years, we've seen a lot of expansion throughout the network, and that has greatly increased site density and ecosystem diversity. So here's that same map colored by the Köppen-Geiger classification. And we're now monitoring many underrepresented biomes and across environmental gradients. So if you're dealing with continuous data gaps are an unavoidable feature of that. So they are filled using standard community approaches, and in Australia we use PyFlux Pro to fill our data gaps. So it includes a routine that looks at selected drivers and then predicts our fluxes based on a standard set of drivers. I've plotted them here on the lower right-hand corner. And there is obviously a scientific basis behind this, okay? So the drivers were derived from equations that are governing like carbon and water exchange, such as the Penman-Monteith equation or the light response functions, and the last Lloyd-Taylor models which we use to partition the net ecosystem exchange, so the net fluxes that we monitor at these stations, into gross primary productivity and ecosystem respiration. So these drivers, they were originally validated on a limited set of the original sites, right, when the network started early on. But we've greatly increased the number of sites in recent years, and our ecosystems are continuously or more frequently operating in a very stressed climate state. So we've actually started to question, like, does the standardized approach that we originally applied across the network to fill our data gaps still hold in the current times and across the large diversity of sites that we're monitoring these days? And we've defined this we've split this into three aims. So the first one is that we first wanted to look, okay, what's actually driving the fluxes? So we have made 4 groups: soil, meteorological drivers, energy, and turbulence characteristics, and we want to see, okay, which fluxes are driven or which groups dominate which flux. And then in the next aim, we want to look at the optimal combination of drivers for each site specifically. And then lastly, we assess the model performance and the ecological implications if we do not use just the standard set of drivers to fill our data gaps, but the site-specific drivers. So our approach uses a random forest model, which is a supervised machine learning model, and we have assessed the relative importance of about 18 drivers. So we cast the net quite broadly, and we included 18 potential variables to drive our fluxes. We then grouped all of these drivers into 4 separate categories to assess the variation in driver contributions between the categories. So we have the radiation components in the energy group. We've got the atmosphere, which includes soil, air temperature, and relative humidity and such. We've got the soil group, which includes soil temperature and ground heat flux. And we've got the turbulence group, which is mostly wind speed and wind direction here. And then we selected all the drivers for each flux that cumulatively contributed up to 90% of explaining the variability in each flux. And then we went through OzFlux QC and we reprocessed all of the data from all of the flux sites on the portal using these site-specific drivers. So that was quite a huge task here. And I just want to show you here that the model, the random forest model, is actually working really well. So it's a very suitable model to identify these drivers. So let's look at which variables are actually driving the fluxes. I don't want to overwhelm you with this picture. I just want to show you the general trends here. So we've plotted the sites that are sorted by aridity index. So towards the water availability increases towards the right. And what is obvious here is that one group tends to dominate each flux, okay? So for the friction velocity, that's the first plot here, is clearly turbulence, and that's expected to dominate the variability. For the latent heat flux, sensible heat flux, and CO2 flux, it is mostly energy, so shown in green here. But you can see that there is considerable variability in the driver importance across the sites. So it's not this one-size-fits-all approach. There is a noticeable variability. And I should also highlight that the little blocks here on the right, these are the agricultural sites that we've plotted separately because they don't necessarily fit into this aridity index framework. But generally, what we also notice is that soil drivers, they tended to be much more important in agricultural ecosystems, whereas energy became less important in water-limited ecosystems. So that is also kind of following our general expectations. Next, I'm going to show you some individual results. So here's one site that we picked that has a nice long data set that you can still see more than just squiggly lines following each other. But for friction velocity, that's in the top row, you're seeing the R value and the root mean square error on the right-hand side. And we can see that there is a constant model improvement if you use the site-specific drivers that are shown in blue over the standardized drivers, which are shown in orange. But we can also see that the model generally shows greater stability. So we're not seeing these sharp drops anymore, or these large spikes in root mean square error. So overall, our standardized drivers seem to be able to handle challenging periods significantly better than the site-specific drivers can handle them better than the standard drivers. And basically, for latent heat flux in the top row or for CO2 flux in the bottom row, it's the same picture. So we have this consistent model improvement, and we have this greater stability throughout the years. Now let's look at some of the diurnal patterns at that site. If we start with friction velocity, you can already see that we got more realistic diurnal patterns. So we've got lower values at night when turbulence is low, and then we've got a more rapid onset of turbulence after sunrise. So this is another indication that the site-specific drivers are better able to capture what is going on at the sites. And for latent and sensible heat and CO2 fluxes, it's not that stark of a difference, but it is sensible improvements. So you can see lower nighttime fluxes of latent and sensible heat, and you can see increase in CO2 fluxes at night and in the early morning, where we do maintain this comparative midday peak in carbon sequestration compared to the standardized sets of drivers. So that's just one site that I could have cherry-picked. How does it look across all the sites in the network? And it's really great that we can report that using these site-specific drivers has improved model performance and accuracy across the board. So at the majority of sites, it's been the R value is better and the root mean square error has gotten lower. We see greatest improvements for friction velocity, for example, at the wetter sites, or at sites that had initially lower model performance to begin with. For sensible heat, it's a bit of a different story. So that's the bottom row here. We do have an initial strong model performance to start with, so there was very limited room for improvement in general. But we actually see a bit of a decrease in accuracy, and that is because if we only selected the drivers that contribute up to 90%, at a lot of sites we only ended up with like 2 drivers, whereas the standard set of drivers was, I think, 5 or 6 drivers. So we're actually reducing some of the information, which results in like a slight decrease in performance of our model. So it's something we can revisit, how much it makes sense to set the cutoff at 90% or not. But again, we see this notable improvement in the model performance at wetter sites. Latent heat and CO2 fluxes overall show through the bank consistent model performance improvements and accuracy increases at most sites. But here we were surprised, or not surprised, we were actually finding that the greatest model improvements were in very arid or in very wet sites. So that is expected when you have either a lot of soil moisture driving your dynamics or a lot of energy driving your dynamics. So that's the extreme end where we were expecting to see this substantial improvements when we deviate from that standard set of drivers. But again, sites with initially lower model performance exhibited the greatest improvements here. So yeah, that leads me to the conclusions. We have the site-specific drivers that produce consistently high R-square values in our random forest model, and that indicates that the models explain a greater proportion of variance in our flux observations in general. But also we do ingest the site-specific drivers into our gap-filling routines, and it substantially improves the model performance indicated by higher R values and lower root mean square errors. We also get more realistic patterns for diurnal trends with the site-specific drivers, and that kind of highlights a very strong indication that this one-size-fits-all approach doesn't really, that there's a clear limitation in this one-size-fits-all approach, and that there are clear benefits into tailoring the driver selection for flux gap filling according to the site and the ecosystem you're monitoring. Overall, the driver importance varied between sites, but it was consistent within climate zones. So that, again, supports the approach that it makes sense ecologically. We also identified key auxiliary variables with our approach for each of the climate zones by having the high importance of drivers for some variables, and that might inform future observation priorities within the TERN network, but also within other networks if they follow this approach. And lastly, we now should consider if it makes sense to incorporate the site-specific driver approach for gap filling into our standard flux processing routines in PyFluxPro. And I'm happy to report that all of the central node folks have been working with us on this project, so this conversation is likely going to happen very soon. Thank you.
Yeah, can we have the speakers back on stage, please? We've only got a short moment for questions, but we have a few. So I might start with a question for Anne. So the question is, for impact, we need to integrate data internationally. Is the standardised approach to gap filling transferable internationally to other observatories?
Well, at the moment, all international observatories are using a standard set of drivers and a different approach to gap fill their data. So this is definitely the start of a conversation that we're having here. We've been shown that it makes a lot of sense, at least for Australian ecosystems, which we already know do not necessarily follow the same rules as a lot of the Northern Hemisphere ecosystems. But there is a push to use a one approach to process the flux data for all sites, and that currently doesn't have a standardized or an individualized approach. So next week at the FluxNet meeting, we will surely have that discussion in more detail.
Okay, terrific. A question for Chiara. Given the additional storage of C in soils is finite, do we know how much C can actually be taken out of the C cycle and stored in the soil long-term or indefinitely?
That's a good question. There are some studies, but I think they're very localized. It hasn't been done on a large scale, so I'm not sure the answer quantifies straight away.
We've got a question for David. On-farm management for soil C may have direct benefits to farmers other than just C sequestration. Perhaps a more holistic view is required in policy that recognises the various benefits.
Absolutely. I mean, soil health, there is really what drives the productivity of these systems. And I suppose that's where a lot of the conversation and the insetting is that these changes that farmers should be doing will help assist in their productivity and their sustainability and their drought resilience anyway. Some of the barriers to that might be that there's a big barrier to doing a certain practice change. It might be cost, it might be financial, it might be education. But, you know, the good, you know, the powerful thing about soil carbon particularly is that it is a win-win. I mean, it's a win for the climate, it's a win for the farmers. But, you know, as has been alluded to, it's not as simple as it sounds sometimes.
Okay. One last question, because we're running into lunchtime, and this is for the panel. So the complexity of understanding all the components here is daunting. Could you see yourselves working together to support more stories for the general community to feel hopeful? And Claudia, perhaps you want to take that.
Yeah, absolutely. I think my work especially will be great in Chiara's model, but absolutely.
Anyone else want to tackle that one?
I think we have to, like, if we don't have measurement to validate and support the models and models to help to understand where we might need more measurement, we're not going anywhere, or we're not doing it effectively.
Well, I think we are. I mean, that's what TERN is, right? I mean, you know, Anne and I work together on the same sort of, like, you know, my data from my sites are on that analysis she did. So that's the powerful thing about having a coordinated network where you're all using similar protocols, is that, you know, the data aligns really well and enables that to happen.
All right, that's a lovely point to end on. Can you thank our contributors to this session? Thanks again so much. And just a reminder that lunch goes until 1, so please be back here just before 1 to kick off for the next session. Thank you.